Okay, so chapter 21.3, and this starts to get at sort of the guts of chapter 21. This is the Aldol edition. Well, we've got addition and we've got condensation. Okay, so this is a summary. I guess I should say summary here. This is a summary of the Aldols. I'm going to do a separate video for simple and directed. But really what we have here, an aldol reaction is an enolate. And this could be the enolate, the book presents it as it has to be an aldehyde or a ketone. I think that's true to technically be called an aldol. But it works for any enolate. So X here, this could be aldehydes, ketones, esters, kind of amides, but watch out. You can't have an NH here, right? And it could be a carboxylate even. You can make an enolate of a carboxylate. It could be a thioester. There's a lot of stuff here. It could be a nitrile. You get the idea. If there's a carbonyl that has an alpha proton, you can pull that alpha proton off and it'll do the reaction. Okay, so the reaction is, the enolate is the nucleophile, and then you have a neutral. So for an aldol then, this does have to be either an aldehyde or ketone. Okay, so this is the electrophile. So the enolate could be an enolate of any kind of carbonyl derivative. For the aldol, the electrophile has to either be an aldehyde or a ketone. I've shown it as an aldehyde here. So the mechanism is the enolate attacks the carbonyl. Remember, the carbonyl's got significant partial positive charge there. So you can push the electrons up on the oxygen. We make a carbon-carbon bond. If we number these, 1, 2, 3, 1, 2, 3. Okay, so the enolate carbonyl carbon is going to be 1. The alpha carbon that lost the proton is going to be 2. The carbonyl carbon in the neutral electrophile is going to be 3, and those are going to come together like so. And remember that the enolate has a resonance structure that looks like this. If you would prefer to draw your enolates this way with a negatively charged carbon, you need to be able to do the resonance structure, be able to keep in mind their resonance structures. But if you'd rather draw them this way, that's fine with me. And this sort of emphasizes the fact that the carbon is the nucleophilic carbon. So now the reaction would be just a little more, probably a little easier to envision. The negatively charged carbon is nucleophilic, and it makes a bond to that carbonyl oxygen, okay? And then that's going to get you, this is not a full, sorry. This is going to get you an O minus, right? The initial result of those green arrows I drew there is going to give an alkoxide. That's going to pick up a proton from somewhere at some point. And if it stops here, okay, so you're going to protonate that. That's the addition product. So this is called an aldol addition. It's just an enolate adding into a neutral aldehyde or ketone. Sometimes, so heat plus acid or base. So you can either do this, you can do this elimination either under basic conditions or acidic conditions, but you can eliminate between carbons 2 and 3 to get an alkene, and this is called the condensation product because it also makes water. Okay, so water comes out of it. And you can sometimes see that. If you run this reaction in an organic solvent, you'll see water form on the sides. At least that's what they saw back when they first started, or when they first discovered this reaction. Okay, so one last time for the summary, and then I'll do another video on a simple aldol. The aldol addition, or the aldol reaction is going to be an enolate, which is going to be nucleophilic, and it could be the enolate of any kind of carbonyl compound. The negatively charged nucleophile, the carbon, the alpha carbon that lost the proton, is going to attack the carbonyl carbon of a neutral electrophile, either an aldehyde or a ketone. That'll give you an addition product that you got to protonate to get the alcohol, And then from there, you can either do a base or acid catalyzed elimination to get what we call the aldol condensation problem. Okay?